Introduction to Statistical Process Control, SPC. Objectives of statistical process control will be, first of all, to alert management to assignable causes. We want to detect as soon as possible that a variation in the process or distribution of some measurement or outcome of a process has changed, and we want to be alerted because we want to know as soon as possible that something has happened in the process, and we want to detect the reason for that change. The second will be to provide objective measure of consistency. We want to measure the amount of common cause variation in the process. First of all, to be able to know how good the process is, but also to know the baseline for the assignable cause variations. And the third, an additional cause, is we want to try and work on assigning causes to variation that currently is perceived as pure randomness, right? And subsequently, we might want to control these causes or maybe eliminate some of these causes so that common cause variation, is effectively reduced. One tool used in statistical process control is control charts. Control charts are graphical tools to statistically distinguish between assignable and common cause variations. And so we will try to actually capture the common cause variation, and then we will try to use this tool to detect when an assignable cause variation occurs. The way they will be constructed is that always time will be on the horizontal axis and some process outcome will be on the vertical axis, and we will basically add new points moving rightwards over time, adding new points for some process outcomes. We will often create the control charts for samples of data rather than all data from the process. And this is usually due to cost considerations. Right? We can't measure every possible unit that we produce for quality purposes. We might want to measure just a sample, and or the same thing with services. We might not be able to ensure quality of every single service encounter, but we might measure a sample of those service encounters. There will be two types of charts that we will consider, or actually two types of tools. One is a pair of charts. The first one is for variables. If you have some measure that is critical, like physical size of a part, or maybe service time in a service, or waiting time for service, we might collect the data and create a pair of charts that are called X bar chart and R chart. They are always used together, and this is useful when we have something that is a variable that we want to control, that is measurable, right? If we have attributes, there are different types of charts, and particularly for binary attribute, which means that a unit is either a defect or not, we will use something called P chart. This chart comes on its own. All those charts that I will show you here are based on the central limit theorem. There are other charts that exist, but we will not include them in this topic. So the central limit theorem tells us that if you take the distribution of sample means, right, means of samples of some units. For example, I have a number of products, right? I'm producing a large number, and I take a sample of n, let's say 10 units or 20 or 30. And then I calculate a mean measurement of some measurement that I'm interested in. Then the central limit theorem tells us that the distribution of those means will be a normal distribution or close to normal, and the larger and the sample size n, the closer to normal distribution the sample means will be. And this is a useful fact because we know something about normal distribution, right? We know that the normal distribution has almost 70% of the random values within 1 plus minus 1 standard deviation, or we know, for example, how likely a value is outside of the 3 standard deviations. So there is roughly 0.1% chance of the value being 3 standard deviations below mean, or more than 3 below, or more than 3 above the mean, right? And so this is useful because if you want to control variability in statistical process control, we do not want to be bothered with all kinds of random distributions of processes that we have, and we can actually avoid thinking about those distributions if we just take sample means, and then if the sample size is large enough, we can just assume that those means have normal distribution, and then we can work with them. Notice that the normal distribution that we expect here has the same mean as the process distribution that we were looking at, or this measurement distribution that we're looking at, but the standard deviation of the sample means will be standard deviation of the measurement that we were measuring divided by square root of n, so it actually decreases. The larger the n, the smaller the standard deviation.